Okay.
Okay. Uh, you
Okay,
can
that's
see my
good.
slides, right?
Yeah, we can see.
So hi everyone. Somebody wants to join.
I asked a Feng's student,
Okay.
Xinyang. Yeah.
Okay. So hi everyone. Today we are going to deviate a little bit from what we planned because while experimenting with some things and to show you today, I ran out of my credit in Google Cloud. So hopefully by next week I'll again, or by today I will again get it, and we can like kind of show how you can actually the concepts we are going to talk about today, how you can actually implement them and train your own models or fine tune based on your data. So today we probably are gonna be mostly talk about we're gonna probably talk about just about the theories. So this is kind of like what I want to talk today. So how to build very simple natural language processing applications using LLM and using a new library called KerasNLP. Before we start, how many of you have played with Keras before or any NLP kind of applications before? If you can just raise your hand in Google Meet, there's option.
I haven't.
What about others? Have any of you have like played with any natural language processing applications before? Be that be like a sentiment analysis or anything, or have you played with the Keras library before?
Keras, yes.
Yes,
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 yes, yes,
yes.
yes. I
Okay, so let me start with that. How do humans learn the language? Before we start, since this is like very like between us, this is not really for everybody. So anytime anytime you have any questions, just unmute and ask me. So yeah, little bit background. So how do humans kind of learn the language? So we learn language not only through reading, but we learn by interaction, we learn by our conversations, and we kind of learn by imitating. Now, some,
Rambiba, can you record this lecture?
yes.
Yes, please. So after that, send it to us. Okay. Thank you,
Okay,
Rambiba.
yeah. So some things which are also similar in machine learning or which we will actually utilize a lot is something called transfer learning. What is transfer learning? So anybody can give me any like pointers?
like I think that is you use your previous knowledge to use in the new domain. Is that
Yes,
right?
yes, that's perfectly correct. Uh, so somebody said they worked in Keras, right? Uh, can you tell me, like, from that background, uh, what transfer knowledge actually means? Like, when you say knowledge, what do we mean about knowledge in maybe like language processing tasks, like for text and something like that?
Um, for natural language domain,
Yes,
that's including vocabulary,
yes,
semantic,
yes.
synthetic, and what else?
I
Yeah,
think
more or
also
less that. So if you look in
I
the
think also
slide,
the tradition or language family. If you have the knowledge on that, then I feel like that can be a good um that can be a good place of structure for human learning of languages as well.
okay, awesome. So, making it more little bit formalized. So, if you see in the slide, this is kind of the like different parts of the language. So, when we say level of language, imagine a sentence. Between that sentence, we have things like semantics. By semantics is like a same word has different kind of meanings. We have syntaxes, which is more important for programming languages, but which is also important for different meaning of languages. When you use a comma, when you use a full stop, how does that change the sentence? And how you also form the language and how it gets pronounced. So all of these. Uh, so Yang probably will be able to relate more. So when remember Yang, when Dr. Verma was telling one day in the class that okay, previously he used to see that the Google Translate was bad, then it became worse, then it became very good, right?
Yes.
So what used to happen is that this kind of like how we define the sentence, how we define the meaning based on these syntaxes, they matter, and how we change the semantics or how we infer those, they matter. Without the usage of those, if we just take it as a just normal words and try to just translate them, then it becomes kind of a like bad translation. So the previous methods used to do that, the present methods do not. For why it's important for us, it a lot of the NLP tasks specifically just for language processing, they share the same knowledge base because it's the same language. So how you represent the language, how you structure the language matters. So if it is a task of sentiment analysis, if it is a task of text generation, even though are very different tasks, if it is in the same language, English, you can transfer some like knowledge from one to other. By knowledge, I mean how the language is represented, how the structural similarities are present. In coding sequence, how you write your bag of words, how you write your code. Those you can kind of like take from one to other. Now, what is a like large language model? Uh, so without going into like proper definition, what do you all think? Like, what is a LLM? What does it do?
I don't know.
I think it at least training by millions of parameters,
Yes.
at
Okay.
least.
Yeah, but that's the training part. So what
Yeah.
does like what does ChatGPT do when you write a question? Like when it gives you an answer or when you gives you it generates any text for you. So you write, okay, write me a poem, or can you finish the sentence? I am very, and then it gives you I am very hungry, I am very happy, I am very excited, something like that. So what happens inside that? So what you see in the slide is very formal definition, but intuitively what actually happens?
I think EVM is based on the search function, but it's more than that. It's give you beyond the search, like a Google search. It can generate more content than just answer the question.
Okay, not exactly. So what happens is that all these LLMs, they're literally your auto completion. So what it does is that it does nothing apart from trying to guess the next word or next letter or next token. Whenever you hear this word called token, tokens are in context of language is the next word it's going to produce. So what any LLM does is try to guess what the next token is. When you write I am very, it will try to guess what comes after very. But that's a very simple explanation. If we go back, it will try to guess what comes after very, but with the knowledge that what is before
Before.
very. It is like what we have before very. It is I am very. It can be like the word can start from only very. So it goes back to the all the parts it has been trained. It sees what are the sentences which is similar to I am very, and all the sentences it finds it generates a probability of okay, I have these many sentences which has the same similar kind of sentence structure, and after the very these are the different words that has been used. It does a probability distribution of all the available words it has, then it based on the distribution, the highest distribution out of its candidate is your result. So imagine if somebody used I am very hungry a lot of times, then I am very excited or I'm very happy, and in its whole training corpus it has looked into all of them, it has created a probability distribution. The highest, the most probable is what? Hungry. So it will give you hungry. Now, if you write something in a different way, it will try to guess that in a different way, even though the meaning is same. That's why every time based on like what we give it, what kind of sentence we write, the same answer differs for LLMs. So that's very kind of like uh, hand wavy explanation of what LLM does, but how are they trained? When we say that, okay, you train in a lot of data, what does the training mean? Like, what is a training? So we will do a hands-on next day, but today you will mostly understand like what goes on inside. So when you do it, when you don't get good result, you can kind of go back and understand that, okay, this is what actually happens inside, and this is like what's going on.
Okay.
So how are LLMs trained? So
uh, using neural network.
yes, but that's so there are different kinds of training. Different kinds of LLMs available. Neural network is just like kind of like a layered approach of doing it, but then a lot of other things happen. So, for example, this for this specific one, we are using something a little bit old. This came out when GPT-3 was there, back in 2020, I think 2020. Yeah. So this is Google's BERT language model. This has been like very popular. A lot of papers you will literally see right now is using this because this is kind of easy to understand and train and has very good, pretty good performance. So what happens is that these are your inputs. So your how, are, and then you see something called mask. We'll come back to that later. And then you are like, there are different words, and then you have different outputs. This mask is where you are like where your variable will go. Like if you are writing I am very excited, then what? That part is your mask. It will try to generate an output based on what your mask is and where your mask is situated. Based on that, it will generate the probabilities. If you see on the up, the you, they, your, these are the probabilities it has generated. And based on that, uh, if you have used ChatGPT or any of these in API, you will see two options present. One is a k value, one is a p value. So those two kind of like regulate what will be your probability, like that you, they, yours. So k is like the big, how big your pool is. Sorry, k is like what amount of the temperature, like what amount of words between your pool it will be taking, and p is the whole pool. So generally you might define like, okay, p is equal to 40, so you have 40 words in your pool. And in the k you can ask it to be as creative, so take the temperature down, and it will try to take the temperature up, and it will try to randomly guess out of those 40. If you take it very down, it will try to take the only one, and it will try to keep that one picking up every time. Any question?
Yes, and what is a temperature?
Okay, so temperature is a mathematical function. I'll go to it later, but just for understanding, imagine you have you have a bowl with 40 different balls in it. So that those are your words. So it has like a plate with 40 different words on it, and you don't have a specific rule to kind of like take what words on it, like which one you will choose. So each of those words has different probability, like different probability of appearing in your sentence, but they all pass a simple threshold. So that was your peeves, your pool. So you passed a simple threshold, so all of them are there. The temperature literally guides that out of those probability, will you take the highest probability, or will you take randomly something that has appeared but that has good chance of appearing. So if
Mm.
you make the temperature higher, then it will take any one of these, like whatever it comes. Or if you take the temperature lower, it will take the highest probability. But by that you define that, okay, take the highest probability. So anytime you ask the same question, assuming the pool is same, it will keep on taking the same output. So you have more or less guarantee your results are gonna be same.
Okay, so when you ask the same question to the ELM, you won't get same answer all
if
the
you
time.
if your temperature is high, because it will try
Yeah,
to take anything. If your temperature is lowest, so all our experiments we try to fix our temperature to 1 or 0, like the minimum available, so
yeah.
that we can at least reproduce. But
So
yeah,
it's really matter how much the pool is, and then you
yes,
can get how many various
even
answer
yes,
respond.
even more than how much pool, what matters is like if the things in pool are same or not. If the pool, even if it is a pool size of 40, if what's coming into the pool changes, so for example in ChatGPT's different versions, they are training with more data, right? So for the same question, next time your pool might have different candidates. In that case, even though your temperature is lowest, it can find a different answer because your candidate changed.
So that make the answer always,
Yes.
you can always change the answer,
Yes.
the response, right?
Yes,
Yeah.
that's why in research we always try to like freeze the models we are training with so that we can reproduce. Otherwise, we will be like ripped apart that okay, it's like your answer doesn't make sense because we cannot reproduce it.
Oh, can you explain a little bit about the
Yes,
phrase?
yes.
Yeah, let me go a little bit more because that will be different. So, in very short, freeze is that you control your model. So, you cannot freeze any like GPT or these kind of things. You fix that, okay, this model has been trained with this amount of data. I am not gonna do anything on that. So, this is my frozen model, and I keep on working on that. As long as you do that, you can still kind of reproduce.
Yes, yes. Go ahead.
Okay, so we have like all the LLMs and everything. We all say that okay, this has been trained on a huge amount of data, but what is that data? Like, where is that data coming from? So, not everybody can create those data, even the big corporations can. How are these open source libraries or like where is that data? So this is that. So this is a paper called Pile. This is a collaboration between almost all like big organizations, uh, including Microsoft, Google, and everybody. So this is like 825 gigabytes of English text. These are like a combined effort of all the different data sets you look on the side. So they all have been combined on this single data set so that people can use that for training, or mostly the organizations can use this for training their LLMs. So just when like what Yang was saying, neural network. So when we say network, that essentially means layers, these neural layers, and how we train them. So on the left is the first kind of paper that came out in 2003, a neural probabilistic language model. So this is what Dr. Verma was saying that day, and this is what like what happens. I won't go into the math too much, but in very simple terms, what happens is that you have a softmax layer. Uh, that's where your output and your context are, and then you have a kind of like scorer function that's in the middle layer, and it just creates a different probability, and you have a lookup table where it goes like takes on that okay, for this input should that be output, for this input should that be output. When I say input, it's literally maybe a word, the output may be the next word, literally just the next word, like what should be my next word, something like that. The context here is the whole sentence, how big or small that is. Now, that was a very simple concept. Take that, go into the right. That's the BERT paper we have been like experimenting with. That GPT also works in a very similar way. So here you have multiple layers. So BERT right now has like 24 layers. So the layer on the left, imagine you have 24 of them, and each of them are connected between each other using a different scorer function that it scores the output that okay, is it good enough or is it bad enough, and discards the output when it's not good enough. So this is what essentially happens. Now going back to LLM, so that was just neural network. What LLM does is that there's something called encoder decoder network. Anybody has heard of this before?
Hi.
Sorry. So
Hi. Yes.
see you later.
Okay,
Bye.
thank you.
Sorry, the decimal just can pop up.
Okay, okay. Yeah. So what happens here is that so the method I showed you, if you just look on the right, you will see how complicated it will become. Complicated means also a lot of computation work. So what a LLM, sorry, what an encoder decoder model does is like what is that the encoder is, so when I said that you will have a different attention, so for each of those scorers put different attention, they have to be rely on the other scorers, so that's what make it more complicated. What the encoder decoder model does is that it can make the attention by itself. So the tokens literally, when it goes out, it looks at each other. So when you get like a next token out, it looks at each other and it changes the attention. That decreases the computational load a lot. And the decoder part is, it takes the target token. Target means the output. It looks at the source and queries the decoder, says that okay, it literally just a key value query, and takes that, okay, does it matches or not. So these are for the same input, same output. When you have what that's gonna be like guessed, that's going to be predicted, that becomes your masked decoder. So that becomes your output whenever you put anything to an LLM. Now, you have heard about tokenization. So what is a tokenization? uh, any ideas?
It's just a chunk the context into the basic unit of word.
Yes. Now, everything we have talked till now, this one, all of these assumes that you are going to predict something on the next. That's something we have always assumed a word, but we call it token. Why that's important? Let's look at this example. When you generate something in ChatGPT, you will be very you won't be very happy if it doesn't give you like a sentence without a comma or a full stop or without a meaning of those. So if there's an exclamation, the word should come with a meaning with exclamation or something like that, right? So how you tokenize matters. So for example, look at these three examples. So we literally tokenize the first one based on rules, based on that, okay, if you have something like that, then let is one token, apostrophe s is another, tokenize is another, just exclamation is another, something like that. So this is how you tokenize one way. This is one way to do that. Then we tokenize based on punctuation, that whenever there is a punctuation, we tokenize based on that. So it's let, apostrophe s, tokenize, exclamation, but then it becomes ISN because isn't is single, but ISN, even though it's not word, we are punctuating in punctuation, so that becomes different. And if we just want to tokenize on white space, then we retain the punctuations and just tokenize on words based on what you're what you are going to do with your LLM. This will matter a lot. For example, the first two are very important if you want to build any kind of actual natural language processing application. But some of you know I work mostly for code. For me, the first two isn't that important. But what is important for me is code syntax. So I tokenize based on certain rules I have created, based on certain semantics of code, certain code specific tokenization. So this idea is important for you to understand what you will do, what is your data, like how you want to do it. Not everything will work better for every result. Now we go to word embedding. So what is a word embedding? Each token is replaced by a vector and its meaning in a continuous vector space. That is a word embedding. Do I have a better slide? Okay, let me just Google out a uh, visualization. Images. Give me a second. Hello.
Yes.
Yes.
এখনো হচ্ছে আর 10 মিনিটে হয়ে যাবে, ঠিক আছে?
Oh,
Okay.
He's
he's a
wonderful.
he's a Francis.
Yeah, he's asking like am I done? I'm like, okay, in 10 minutes. Wait. Let me find a, like there is a good example which I like, which is of course now I won't be able to find. Uh, I give this example everywhere. Okay, yeah. Okay, so what is a vector space? So if I ask you a very simple question, I am a king, just a king. Okay, if you take, I just ask you something like this. Let me open my notepad. Oh, okay. You cannot see my notepad. Anyway, if I do something like, let's go back here, share this tab, small, yeah. So what will be the answer for this one?
Queen minus woman.
Not really, but why do you say that?
Because a king pair with queen and man pair with woman.
Okay, that's an intuitive answer, but that's not like how it will work. So, what happens in a vector database is that you have numbers attached with every word. So, king has a value attached to it, man has a value attached to it. Okay. So what happens is that look at the share this tab. Yeah, look at this example. So imagine, so these are all vectors. So like what we learned in school. So vector, scalar, and vector, right? So vector has both its value and it's a direction. So it's a two dimension. So king and queen, they all have a value for direction and all have a value for its own like value. So that's the vector points here. So king is 0.5.7, omen, man, these are there. So when I say king minus man, so what happens is that king
Oh,
is
zero.
point, yes, and zero point 0.7 minus zero point 0.2. So literally these are the kind of differences. So what happens is that when you do king minus man, the result will be what? Zero point 0.5, zero point 0.5
Minus
negates zero
point
point
two.
0.7, zero point 0.2, so it's zero point 0.5. So the
Right.
result will be 0.00 and zero point 0.5 here, right?
Yes.
But in vector like negation, this one won't matter, so it will just be this. So now
Yeah.
you have something like zero point 0.5 and like 0.5 here.
Mhm.
So that will be more than here, somewhere here. So less, like that will be near to here. So that will be what the queen's difference will be. So that's how you calculate the difference. So this is man and omen. This is queen and king, right? So
Yes.
when you take those out, so that's how. Let me share this tab instead. So that's how vector databases work. So when we say word ending, what we do is that we take our text corpus. What I mean by text corpus is that these all text, like each token is broken down into smaller words. Take this whole like word, and then we tokenize it. When we tokenize it, each of that sentence become like separate tokens, which can be word and token. These are then put in a vector database, which for each of them they will have two values, like how you saw there.
Right.
Okay, now what happens is that when we, I'm not gonna explain that too much here, but look, I'll just tell you what happens when you search on it, and this is just called semantic search. It's not even what LLM does. When you literally search for certain like king, queen, whatever, it goes into that vector database, like looks for the word, and it tries to see whatever is near to it. So king had queen near to it, and all the other parts, or queen or man had woman near to it. So it also finds what are the other words near to it. That becomes its new word pool. And based on that, next time when you ask something, it will try to answer based on the word pool it has based on the vector database. Okay, that's how it finds the relevant words, like relevant things based on what your input is.
But how in the beginning, how you give the
Number.
vector
Yes.
value to each word, each token?
Yeah, I'm getting there. I was. Any other question? There was one, I think.
Same.
Okay. Okay. So how we define the vector values? That's based
Yeah.
out of, yeah. That's based out of, actually there is like existing, that has nothing to do with LLM. There's existing algorithms to do there. But in a very short sense, remember Yang, what Dr. Verma was telling about WordNet.
Well, what did they say?
WordNet.
WordNet, yes.
So,
Ah,
so imagine we have these dictionaries, like huge dictionaries, which has a relationship between word to the other word, and based on that. So it kind of creates that based on that. Okay, what word is near to what, and based on that, it creates a vector database. Now there are different algorithms to create this vector embeddings based on like what language, because as you can understand, this will vary based on languages, and for non-language things it will vary even a lot. For example, code and stuff, we just go for like something else. But that's how you kind of create those. But it
yes.
also is dependent on your text corpus, because it will go into your text, it will try to see what word is has been used a lot, so it uses algorithms like word of bag, and to see how many times it has been used in one place. That's how, based on that, it gives you the scores.
Mhm.
So today we are gonna stop a little bit after that, after like defining like what we have learned, how we choose the LLMs based on that. So when we compare different models, it's kind of important to consider their architecture, the size of the model, training data, and performance. What does this mean? Yeah, because you have been playing with LLMs, right? So yeah.
Choose between ELM.
So
Um,
imagine, I'll tell you why would you choose ChatGPT. So for what task would you choose ChatGPT? For what task would you choose DALI? For what task would you choose GitHub Copilot? So
it's
these three.
depend on my
Task.
my task. What kind of things I want to get from ELM.
Yes. Now, these three are obvious examples, because one generates an image, one generates like text, one generates code. I would argue text and code falls in the same family, but still. But imagine go a little bit more digger. So these are obvious examples, based on your task. But if I say, okay, it's the same task, now you have like 100 of LLMs, like how do you choose between which one? Here, it becomes that some LLMs might be better performing on certain tasks and not that much in certain other tasks. So here, what you will have to take care of that how much the training data has been used. So these are the different parts which are told, like 20B, 5B, 15M. So that means 20 billion parameters, 20 billion tokens. That means literally 20 million, like, now tokens are not necessarily words, but whatever they have used for tokenization. So 20 million of them has been used to train. Now when you have 5 billion, then 5 billion has been trained, 20 billion has been trained. So ideally, the very simple rule till now has been, the more data the LLMs are, more better. But then you have other considerations, that okay, how fast it is, how, like, can I train them, like can I fine tune them, because the more bigger they are, the more huge computationally expensive they are. So these are how you kind of choose it. For example, this talk I actually created for giving to like developers. For them, choosing LLM matters a lot, because you cannot build an application just because, okay, I can run this 20 billion model, this is best, but the amount of money it will take to run, and you cannot also package it with your application, so it's not like feasible in real life. So you have to choose what kind of things is better for your task. So based on what that's, you will use that knowledge to kind of choose.
Uh,
Yeah.
I have a question.
Yeah.
When we're talking about how big this ELM is, we always talk about how many parameters is being trained, right? But
Yes.
we don't say how many token it can recognize, right?
Not really. So yeah. So when they all say that these billion parameters in bit, so that actually includes those tokens. So when they say 20 billion, that's actually, those parameters include the tokens. So that's
So
why the data size is increased. Yeah.
parameter is has token in there, and but also has other things, right?
Yeah. So
What else?
ideally, yeah. So ideally, in machine learning world, parameter means something completely different. So they mean like the different things you tune for, like tuning your machine learning model. Definitely not LLM. Tuning your machine learning model and everything. But in context of LLM, this encodes like what every different parts of it, like the tokens and all of them. Okay. So when we go for applications, you all know, so this has been used for everything almost like language translation, chatbots, content creation, text summarization, and there are other usages like improving search engine, voice assistant, virtual assistant, all these. Uh, my personal opinion is LLMs are mostly very good at synthesizing. So creation, kind of like generation and all those, and less potent for actually searching things or those. We have to do a lot of different kind of tricks to make it better for those. And we will cover why they are not important. We will actually try to do that and see how good or bad that is. So some of the examples we have is if you see on the left and right, so these are different like models we have. So Elmo, GPT, BERT. Remember, this is the first GPT in 2018, then GPT-2 in 19, then GPT-3 in 20, and now we have 3.5, 4, all these. So these are different kind of organizations which have trained these models. Anything interesting that's coming out from this slide?
The training size is increasingly by time, by date.
Yes, so that's one. So when people realized that all you have to do to make it better is just throw more like training
Data.
data to it, and it till now has increased. So that's what they have been doing. There's one other very important, or like for me, it was very interesting aspect is that if
Tell
Um,
us.
the largest one is the Megatron,
yeah, that's
and that
because
is Microsoft and NVIDIA.
NVIDIA.
That means they have not only the they have huge resources that they
Yes.
can
Yeah.
utilize,
Y-
leverage.
Yeah, but one like very interesting aspect of all this is that you will realize, even though we are talking about research, since last 4.5 years, all these, you don't see a single university name here. All of
Oh
them,
yeah.
all of
Yeah,
them,
they are
Yeah.
industry.
all of them are
Big tech.
industry. That
Yeah.
kind of gives you an idea how much money you
They
take to
yes.
and the
So
barrier of entry.
it's burn money.
Yeah, so that's kind of also brings into the different talks I give that okay, how we bring the barrier of entry less so that other people can also kind of use that, not only these
بس انت
corporations.
لازم تحلها.
Okay, so I think we'll stop here. I'll just give you a
Okay.
glance of like what we will cover.
Yeah.
Maybe we can cover it before even because I think this will be important. So we will cover. So next we actually jump into
Yeah.
the Palm 2 model, which is Google's. So Google now has two foundational LLM models. One is Palm 2, one is Gemini. Gemini is the latest one, which is like GPT-4 compatible, like similar performance with GPT-4 and beats in some cases. But that's also multimodal, so it can understand images, it can understand video, it can
Good.
understand all those.
Off.
Yeah.
The Palm 2 was just the one before that. Palm 2 is mostly comparable with GPT 3.5. And
Okay.
why that's important is that if you build applications using Palm 2, it's going to cost you less. And for
Oh,
most purposes, like how you have seen, GPT 3.5, ChatGPT is good enough. So for most purposes, Palm 2 is also good enough. So if you want to keep it into less, this is very good choice. This has very like different models, and we will go into that. Okay. Yeah.
The Gemini, is that open now?
Part of it is open, so we will actually use Gemini as well. Before I cut off, let me just show what we want to talk about next. So we will talk about Palm, then we go into like the libraries that okay, how Keras fits into that, how we will use Keras. Then we'll go into a little bit of like using the APIs, and these we will actually do. So next time we will actually use our
yeah.
laptops to kind of like train a very small model, and we'll also train a very small transformer model from scratch. So you have idea
That's
to
great.
Great. Yeah.
yeah. So
Send us from Biba the PowerPoint so we can read it ahead so we can understand everything before that.
yeah.
Yes, that
Yes.
will be
Yeah.
great.
Share it with us. Thank you, Ramit. That's awesome. Thank you
Okay.
so much for everything.
Yeah, that's great.